This is an AC circuit lab done in TAFE New South Wales for series RC circuits. Continuing on with last week's lesson and considering a series RC circuit, today we start off with a series resistor and a shunt capacitor on the output of our circuit. We'll be using the oscilloscope in two-channel mode, and we'll be using channel 1 to measure the supply voltage, and we'll be using channel 2 to measure the capacitor voltage in the circuit. And if you think about this circuit we should see the source voltage, the supply voltage, actually leading in time the voltage that we measure across the capacitor. And I'll demonstrate that in just a second using a phasor diagram. But let's explore the circuit a little bit more. We have a 900 Hertz supply voltage at 4 volts peak to peak, and that's coming through the series circuit, developing a voltage drop across the resistor and developing a voltage across the capacitor. And the voltage across the capacitor, of course, depends upon the frequency of the circuit, and in this case we're using 900 Hertz. If the frequency was above or below that, that would dramatically change the voltage appearing across that capacitor, as we talked about last week. And that's based on XC of the capacitor in this circuit. In the laboratory, you're asked to complete a table for the voltage across the capacitor. You'll have to convert the voltage to RMS. And of course, peak to peak to RMS, don't forget you've got to divide the peak to peak by 2, and then you've got to multiply it by 0.707 because this signal generator is set up to 4 volts peak to peak. VS, we have to measure the supply voltage on channel 1 and again convert that to RMS and record it here in the table. And over here, VC as an angular difference between VS in degrees. So like I've drawn here, we should see that the VS is actually leading VC on the oscilloscope, and I'll add the oscilloscope diagrams. I'll add the oscilloscope waveforms to the video after when I put the video together. Now, if I draw a phasor diagram for this, and we label the axes. This would be VR, this would be VC. There's always, of course this is also the circuit current. ICCT, I circuit. So there's no phase difference between the circuit current and the voltage on the resistor. So therefore they're both laying on the same axes on the phasor diagram, and the voltage on the capacitor is always going to be 90 degrees lagging the circuit current for reasons that we showed in last week's video as well. And of course the resultant that we get here is going to represent the supply voltage, VS. And if you look at this phasor diagram now, you can see that as the phasor is rotating counterclockwise, the circuit current is leading the supply voltage, that is, the resistor voltage is leading the supply voltage, and the supply voltage is leading the capacitor voltage. And that's exactly what we've seen here on the oscilloscope. So we end up with two angles. We end up with what I'd call θ1, and we end up with theta. And of course, theta here represents the phase angle of the circuit. And the phase angle of the circuit is that which the supply voltage is different to the supply current, the circuit current. So in this case we've got a lagging phase angle in a capacitive circuit, and that would be designated with a minus if we did some maths on those figures. To work out the phase angle in the circuit, of course, going on from what we saw last week, that was that the tan of theta is going to be equal to the opposite over the adjacent, and therefore that would be equal to VC, that's the opposite, over the adjacent, which is VR. And I can't quite squeeze things in. I'm going to run out of video space there, so look, I might just swing up to the top of the board. To rearrange that equation then, we'd have theta equals tan to the minus 1, that is inverse tan function, times VC on VR. And that's going to give me this angle here. Of course, in this first part of the lab today, we're looking for the angular difference between VS and VC, so we're more interested in this angle. And if you think about it, that would be 90 degrees minus theta, 90 degrees minus the phase angle is going to be equal to theta 1, which is the angular difference between VC and VS. The end of section 1. Here's one of the students has wired up the RC circuit, and I can see the 1 k ohm resistor and the 1 microfarad capacitor there. And just having a bit of a glance at the lab sheet there, and going through and doing some calculations. Looking at the oscilloscope, I can see the two waveforms. Good, I can see certainly some separation between the VS and the VC taking place there. And checking the signal generator, we have 900 Hertz. So now it just comes down to the students to measure the phase difference on the oscilloscope, and they've been trained how to use the cursors on the oscilloscope to accurately measure that phase difference. And then they'll take that phase difference and they'll do some maths with that to convert that to an angular difference out of 360 degrees. Make sure to see part 2, where we go on to explain this further and draw the phasor diagrams on the board and have a closer look at the oscilloscope to see the time difference between the two waveforms.